Hi, and welcome to my talk. I'm Käldström, an upper secondary school student from Finland. You may also know me as the Kubernetes on ARM guy, which was my first project that I launched 1.5 years ago. Yeah, I'm from Finland, and I'm speaking Swedish as my mother tongue. Some people in Finland do that. And I'm a maintainer of Kubernetes since a year back, which I'm really excited about, and I'm excited to be here today. A funny thing to know about me is that I've never taken a computing class. I've just tried to learn from the internet and from the community, from others, from you. And what have I been doing then? My first open source project, as I said, was Kubernetes on ARM. It was a really easy solution to run Kubernetes only on Raspberry Pis initially. But I didn't like it to be a side project in my own GitHub domain, so forth. So I simply merged it into core, and that was pretty exciting. That happened a year ago. And I followed that up during the summer, last summer, and wrote a multi-platform proposal, which is about 10 pages long. You can go and check that out for more details on this subject. I've also worked and maintained Minikube for a while until I moved on to kubeadm. And, well, since August, I've been doing a lot of kubeadm stuff, maintain that, and I'm really excited about the 1.6 release now as well. What am I going to talk about? Well, this that I have on the table here. It's a cluster with 3 different architectures, 3 different platforms with nodes of Intel and ARM, both 64 and 32 bits. So, and I'm going to show how to run a Kubernetes cluster on them, combine them into a single unit, and abstract away the differences that one particular node may not be able to run all binary. That, for example, Intel binaries can't run on ARM nodes and vice versa. So basically, I've divided my talk into 4 parts: what, why, how, and what now. So we'll start with what am I talking about when I'm saying multi-platform, for me at least. Well, briefly, when I'm talking about multi-platform, I mean both the ability to run Kubernetes on a Raspberry Pi, for example, or run another machine that isn't Linux and Intel, which is the default one, and it's the most production-ready one, obviously. But also, I want to show that it's possible to mix these platforms in the same cluster. For example, it could be also Windows and Linux. That's the same thing. But still use it smoothly. Kubernetes should abstract away these differences. And as long as you're providing binaries for all architectures, it shouldn't be a problem. So a quick recap. How can you do this? For example, with Go. And you can cross-compile pretty easily with Go. That's one of the good things with the language. For example, you may just to make an ARM binary that's with Go that's statically compiled. You just set Go arch to ARM, or you set Go arch to ARM64. If you want to make a simple main Go or whatever binary for Windows, you can set Go OS to Windows, and it will make a such binary for you. So that's pretty straightforward, but there's a lot of different, it can be much more complicated. For example, if we're using CGO, we have to get some cross-compilers, some GCC cross-compilers for the right language. So in the other example here, where cross-compiling a Go binary that has CGO code in it and linking that as well. Then what Kubernetes is doing today, and basically Google doesn't have any other than Intel. They only have Intel hardware for the CI right now. But still, we're releasing Kubernetes binaries for ARM and for ARM64. And with the new 1.6 release, we're also releasing binaries for PowerPC 64 little endian and S390X. The latter two, I've never used them, but still, people from the community have contributed and stepped up. That has been really great to see, the interest there. Also, it's possible to do emulation with Linux. So I can run ARM binaries on an AMD 64 host. And I can build Docker images as well. And when an ARM binary runs in a container, for example, with Docker build, just if I put an Intel binary inside of the container, which is QEMU, I can register a module in the kernel. So the ARM binary will be translated, the ARM syscalls will be translated into AMD 64 ones when using QEMU as the layer in between. And this approach is used now with all the builds, all Docker builds for ARM, ARM64 and so forth. And this is pretty convenient because, well, we can have official builds without having to do anything else, just straight from Google CI builds. So what has the journey been like? Well, 1.2 was the first release I participated in. And there I made initially ARM binaries that were released. And it was a huge step for me personally, at least to get that into core. Then I continued in 1.3 and made the Docker images with this QEMU approach as well. So after that, Kubernetes could release both ARM32 and 64 bits, and also the Docker images like Hypercube, for example. So you could run a cluster from official binaries, official everything, with 1.3 on an ARM machine. How many of you have used Kubernetes on ARM, by the way? Really cool. That's awesome. And also, when talking about scheduling, it's a little bit difficult if we don't know, if the kubelet doesn't say I'm an ARM node or I'm an AMD 64 node, we can't schedule on it. But in 1.3, the kubelet registers itself with a specific label, and we can then schedule based on this label. This isn't like the recommended approach long term, but it's possible to build on top of this for more advanced mechanisms. Then in 1.4, kubeadm was released, and I'm very excited to see this simple and straightforward flow with kubeadm. And as I said, I worked with the SIG cluster lifecycle team from pretty from the beginning. And this cluster that I have here as well is running kubeadm, and it was just a matter of some straightforward commands with init and join. In 1.4, unfortunately, we had to patch the Golang because there was some bug in the runtime. So we had to patch it in order to get ARM working, but this affected only the ARM 32-bit builds. But 1.4 worked on ARM with that patch, and it could be removed in 1.6 when the problem was fixed with Go 1.8. Then, as I said, the community has been really great, primarily here from IBM with PowerPC, 64 little endian, and S390X. And in time for 1.6, they contributed builds for these architectures as well. And now it's really cool because it's mostly a matter of like adding to the list of supported architectures in all makefiles, and that's how it should be. And yeah, if you have any questions, it's just to ask. So why should Kubernetes work on multiple platforms? Isn't that like the too weak Raspberry Pi, for example? That doesn't make sense. Or how should we look at this? Well, we have the CNCF charter, which states this pretty well. And yeah, I totally agree with this, and think it's for the diversity of machines and for the future ecosystem with cloud native, it's important to include all architectures and all platforms. And by that, we'll see a stronger competition and so forth. Also, there's a great quote of Brendan Burns in a newly released article, where he also states that we shouldn't make this an Intel AMD 64 exclusive thing. Instead, if we have more architectures, we'll see more diversity, both in the use cases and yeah, we'll see a stronger ecosystem. And we don't know in 20 years if Intel will be the dominating platform. It could be, or it may not. We don't know. And if we get 4 new architectures, platforms, to the Kubernetes ecosystem, we'll get some more people with it, and that's great. And the risk of vendor lock-in will be significantly reduced. So if we force 5 architectures to be built on nearly every build, we can't make features that are for one platform only without breaking the CI. And that's how it should be. And this means we can't easily, even without noticing, break things. What could Kubernetes on ARM and just ARM 32 and 64-bit be used for in the meantime? Well, we have a master thesis from these guys here, Kasper Nissen and Martin Jensen. They wrote about a year ago from my project Kubernetes on ARM. They wrote a 163-page master thesis about this, how Kubernetes, how anyone could teach Kubernetes the cloud-native concepts and so forth to students. And this is a thing I'm really excited about. We want more people to be able to adopt these technologies. And when having a Raspberry Pi cluster, for example, it gets really practical. I think I've seen 2 or 3 here downstairs, and from the vendors, they've built their own clusters and are having fun playing with the small ARM machines. And this project went well, as far as I could read. And I hope we can continue educating these things and maybe providing some official material as well. Also, ARM 64-bit could be a thing in the future. For example, now the first 10 nanometers processor was released from Qualcomm some months ago. And, well, Microsoft or other vendors could use their in the clouds if they want to. We'll see. And then also, as I said, in classrooms, the even younger students could use, are already using Raspberry Pis in education, for example, in Great Britain. They've had great success with using the Raspberry Pi as education material. And we should have this for Kubernetes too, with the Kasper and Martin's material, and maybe something else. Also, some of you may have heard of packethost.net, and they are providing a pretty beefy machine with 96 cores and 128 gigabytes of RAM for a pretty cheap price. And this is the new KVM Thunder X processor. And I think this could be used for enterprise workloads as well in the future, or maybe even now. So how do I say, well, now that you want to use Kubernetes on your Raspberry Pi or your whatever ARM device, how do you do this then? Well, use kubeadm. It's a really easy and straightforward tool. How many of you have heard of kubeadm? Cool. Nearly everyone. Basically, you're first trusting the Google apt key. This will be changed in the future to the CNCF when we'll host our packages on CNCF infra. But for the meantime, it's Google that is kind enough to sponsor this. Then you can just apt-get install kubeadm, and it will install it. And if you want to bring up your master with all the defaults set, just issue kubeadm init in the command line, and boom, you have a master. Then you should apply a pod network. Kubernetes is extensible, so it doesn't come with a default pod network. Instead, third-party providers like these one downstairs may come up with their own solution that are conformant with the CNI spec. And in this case, I'm using Weave, which has built-in support for ARM and ARM 32 and 64 bits out of the box. And Kubernetes shouldn't have different install paths. So if we're having 5 different install paths for 5 different architectures, it won't just work and will lead to sprawl in the ecosystem overall. And now you might think, how does this really work under the hood? And since this is a deep dive, I'm going to go into it a little bit at least. Kubernetes releases, as I said, server binaries for all supported architectures, and also for Windows, now that SIG Windows has done terrific work with the kubelet and kubeproxy, so it's runnable on Windows as well. And these are released and uploaded to a GCS bucket and easily downloadable. Then all Docker images in the core Kubernetes Docker repository are built and pushed using this QEMU emulation method. And there is a semi-standardized makefile. So basically, when I ported Kubernetes to ARM the first time, I rewrote the makefiles we're using, and now it has been copied and being used as the base for new projects and new images as well. And Debian packages are built for all architectures, and this is pretty straightforward. It just downloads the binaries from the GCS bucket and creates some debs. And then finally, kubeadm is aware of which architecture is running on and generates manifests for the right architecture. But this is a thing I don't want to do in the future, because it gets very cumbersome if you have 3 different platforms and you want to run a workload my cool app, for example. And I'm building images, I'm building the Go binary, and pushing to Docker Hub. But then I want to run it on this cluster, and whatever I choose, the scheduler could, if I choose to do a kubectl run, and my cool app, AMD64, if it then lands on a ARM machine, it won't be runnable and will fail. So ideally, I would just say my cool app, and whatever architecture it's scheduled to, it will choose the right one. And this is possible. And Phil has done some great work on this topic, and the other Docker registry guys. And Docker registry version 2, schema 2, supports this. And it's called manifest list. So a manifest list is a, list that specifies that for this platform with these properties, the layer that should be used is this one, as basically a reference to another image. So if we're pulling a manifest list from an AMD64 host, it will choose the AMD64 image, and so forth for ARM and ARM64. And unfortunately, this, GCR.io, the Google Container Registry, doesn't support version 2 schema 2, at least not fully. So it isn't possible right now to use it for Kubernetes builds. But where I think the movement here is towards CNCF repositories also on the container and Docker image side. So maybe, and eventually we'll have CNCF repositories, which I hope will support schema 2 as well. And also, we don't have any Docker built-in tooling yet. Phil has a repo with a tool, a manifest tool, that can push images. And you're basically saying which platforms you want to push for, then specifying a template. And that template will Arch and OS will be replaced with the real content. And then, in this case, looks as my app version 1 will be pushed as the manifest list. And for every architecture I've specified here, it will redirect for those supported platforms. And then we have a demo. Here I have 2 up boards in this cluster. Up is Intel-based board, costs about $100. I think they're made in Netherlands. Then we have Odroid C2, 2 of them, which is ARM64. And we have 3 Raspberry Pis. of the version 3. And in this cluster, I've run kubeadm init and joined the rest of the node. And all these instructions, you do this as well. The instructions are available in this repo. Basically, I'm doing this. Kubeadm init, kubeadm join, very straightforward. Then deploy just with kubectl apply the rest of the images. So I've built under my looks as domain a lot of manifest lists for this with manifest tool. And then I'm using those images in the Kubernetes YAML files. And then it's just a matter of kubectl applying them on a fresh cluster. The Kubernetes dashboard is up and running, Heapster. I'm using Trafic as the Ingress controller, because this is bare metal. I don't have an Ingress controller by default. Also, I'm behind a firewall. I don't know really how the network is set up here, but I'm using ngrok as the proxy. So I have a public IP address, not IP address, but I have a public domain to the internet to showcase this on, and it's great for hybrid clusters, especially for demos. Then all the metrics data in the cluster is stored in InfluxDB and can be visualized with Grafana. And it's Heapster that's pushing metrics, CPU and memory metrics to Influx. Also, I'm using the Prometheus operator for from CoreOS. And Prometheus itself is multi-platform as well, which is really great to see. And I'm creating a Prometheus third-party resource in this demo. And then in Kubernetes 1.6, we have a new feature where you can autoscale on custom metrics. This is alpha, so it's not stable yet, but I think the plan is to make the custom metrics API beta in time for 1.7. So I'm bringing this up now because I hope you are interested in hacking on Kubernetes, and this is a great place to contribute as well. Alpha APIs are the best one to test out and try to see if you find some limitations or you want to change something and be involved in the process. And then we'll have a better Kubernetes when it API or functionality when it reaches beta. And a sample app that serves a metrics endpoint. And autoscaling with custom metrics is possible. And it's not possible really with 1.6, so, or at least it's very complicated. So I've had to cherry pick a PR on top of Kubernetes 1.6 in order to do this demo, but it shows the possibilities to try this flow out, and I wanted to demo it because it's quite cool, and I think, well, this is a deep dive, so it's for hackers and makers of Kubernetes. Basically, the Horizontal Pod Autoscaler controller asks the API server for the custom metrics API, which indeed is running on cluster. And this is a service, just a normal service that speaks the custom metrics API language. And my custom metrics API pod is asking Prometheus for information, and Prometheus scrapes the metrics. Let's see if we get this working. So here is my cluster. I have right now 6 nodes connected to it. And I have 2 AMD 64 nodes, 2 ARM 64 nodes, and 2 ARM 32-bit nodes. And I don't have to care at all about where these pods are running. They are just running somewhere in this cluster. And I mean, in this case, for example, the Prometheus operator is on the up board, but here we have Kubernetes dashboard is running on a Pi, and so forth. It's just whatever the scheduler chooses as runtime. Then we have kubectl get horizontal pod autoscalers, and we have 1. Now there's coming 8 requests a minute to it, but if we do some load, make some load to the metrics and the sample application, I hope we'll see an increase in some minutes. Also, here is the Kubernetes dashboard. I think it was running on a Pi. And we can query for everything just as usual. Also, Grafana is running. And I can take a look how the cluster is performing, which is really cool. And as you see, this is on a public domain, a subdomain of nginx. So although I have it totally private, I've exposed it to the internet. And here is my sample application. Doesn't say really much, but live demos and over Wi-Fi. 50,000 requests, and this sample application exposes a metrics endpoint. If I could get that right. Cool, there we go. And we can go back and see the Horizontal Pod Autoscaler. And now we have replicas 4. So based on some custom metrics that were exposed by the sample application, I could autoscale a cluster here in real time. And now again, it doesn't matter where they land. The scheduler just increased, the controller manager just increased the replicas, and they were scheduled maybe on some Pis or whatever. And this makes it possible to really do mixed workloads in the same cluster. And yeah, I encourage everyone here to try also offer features out if you have time. It's pretty cool to follow the strong development of Kubernetes. And you can try it, for example, with this. And lastly, the roadmap. I'm working with the CNCF team to make sure that we have CI for ARM and ARM64 in the future, and maybe PowerPC and S390X as well, and to extend the CNCF cluster, and then make sure other CRI compliant vendors are supporting manifest lists. And it would be cool to create an admission controller that automatically does the scheduling for you. That was my talk. Do we have any questions? Yeah. Do we have any mic or something? Yeah.
So do the end-to-end tests for Kubernetes itself run on ARM hardware these days, or?
Yeah, at least something of the conformance tests run on ARM hardware, but still, someone's got to pay for the hardware if we do automated CI. But yeah, I hope we could do automated CI for all platforms, but still the coverage should be increased, and that's something I would be really grateful if some of you could contribute to this. It's a lot of tests. We have a lot of tests and images, and it's quite a lot of work to convert all the 20, 30 images we have to all architectures, but that would be really cool. Thanks for the question. Well, then, thanks.